Hi guys, Assalamualaikum warahmatullahi wabarakatuh. I am Nabilah Khairani Binti Kharul Saleh. My matrix number is 212023. With my friends Eleshaa, we're going to present about Laplace Transform via Partial Differential Equation (PDE). So I'll be explaining the introduction and the principle for this topic. So I hope you guys enjoy our presentation. So yeah.
Partial differential equation is a differential equation in which partial derivatives occur. It contains one or two or more variables in which the partial derivatives are respect to the variables. It is widely made use in mathematical model for physical phenomena such as heat equation and wave equation. The final product of PDE is where both sides of linear form is identical. The characteristic of PDE is homogeneous where there is dependent variables and non-homogeneous otherwise. The solution of PDE stands with the general solution, which contains number of arbitrary independent functions that equal to the order of the equation, while particular solutions are acquired from the general solution. Different goes to singular solutions, which cannot be obtained from the general solution. A boundary value problem that contains PDE solves all the equations that satisfy the condition, namely boundary conditions. Lastly, existence and uniqueness theorems are the theorems that are related to the name itself of the solution. So this is the meaning of the PDE. To simply put, the Laplace transformation contributes by making it easy to solve a differential equation by using the algebraic form of the problem. And these are the steps of generating Laplace transform. Equation 1 shows a general linear PDE of order 2 in two independent variables stands with a, b, c, d, e, f, and g are the functions of x and y. Equation 2 shows how we are going to get the nature of the equation. This is second order linear PDE forms. The c in equation 3 is constant while t is time. X, y, and z are the Cartesian coordinate and the dimension represent the coordinate number of the equation. Based on this table, wave equation can be classified as hyperbolic, heat equation falls under parabolic, and Laplace equation number 2 as elliptic. Equation 4 shows the equation of integration of mathematical from the mapping f, x to y. Laplace transform we present as L. The kernel of transformation is known as the exponential in equation 6, where S stands for the subsidiary equation and t as the time when ft is equal to 0 if the time is lesser than 0. Equation 7 is when the equation is put under restriction, where c is the constant, ft must not exceed the exponential function on the right side, and it must also be piecewise continuous. The linear operation for Laplace transform represent the equation below, where ft and gt were Laplace transform with e and b as constants. So, with a few mathematical process, we will get the equation as shown. Moving on to PDE in Laplace transform. So this is the basic Laplace transformation, where the kernel involves the transformation of ODE into arbitrary equations and PDE into ODE. The two terms mean the linear operator of the function and a term which refers to an integral transformation of the kernel. By using equation 9, linear differential equation can be solved. With z as a complex plane, if omega is equal to 0, so it is as the exponential equation. If s equal to 0, the equation is as the equation 9. If kernel have the real part, so the Fourier transform is referred as the complex plane. To make it simple, equation 10 contributes for the condition to the integral in equation 5. It can also be denoted as equation 11. To prove it is to make an ft to obey the conditions above. Then Laplace transform of the fs that exists for all Re s is bigger than a as equation 7. In equation 13 below shows the integral evaluation takes s minus a is bigger than 0 as assumption. Fs exists and is bounded above its magnitude. Equation 14 is a derivative of function ft of Laplace transform, while equation 15 is the equation that obtained from the second derivative of ft. In Laplace transform, it is required for us to know about the basic inversion formula. This section shows how we can deal with the sophisticated problem. So let's take a look at Cauchy integral formula, where the value of a holomorphic function inside a disk are determined by the value of that function on the disk boundary. Function u to c is holomorphic and that c is a circle contained in u. Then for any a in the disk bounded by c in equation 17. Equation 18 and 19 is proven that the Cauchy integral formula can be applied with the equation 16. Equation 20, if the inversion integral of f converge and if I present. The following contour marks the application of the Cauchy integral formula in the integral. If f is a complex variable s function that is analytic in the half plane, a is bigger than s for all s complex plane, and fs with real value when x is bigger than a, and by letting the k bigger than 1, m and r as constant, such as fs, k is smaller than m for s bigger than r, and the half plane x bigger than a, then the inversion integral of f along any line x equals to the terms defined by equation 24 that converge to a real valued function t. So this equation tells about f as being analytic and is real in the half plane a is smaller than s. Based on Schwarz reflection principle, fs is equal to fx. Since fs is analytic and fx is real in the half plane x is bigger than a, the inversion integral will show as equation 26. After that, by applying the condition given above, equation 27 was obtained.
Assalamualaikum. My name is Eleshaa from Chandrasekaran. My matrix number is 21390. Today I'm going to talk about Laplace Transform. Laplace Transform application and an example. Laplace equation is widely used these days, particularly in the study of classic electricism and gravity, as the other answers point out. In reality, a considerable section of an upper level E&M circular at the undergraduate level is devoted to find solution to a Laplace equation under various boundaries, condition and application. So the electric potential, which is a crucial variable because it can be quickly calculate the electric field E equals to V and the force F equals to QE. Is obtained by solving Laplace equation since it's only applied to areas with zero charges density. Now, the application may apply to data mining or machine learning with the help of training data. Machine learning focuses on making prediction based on known properties. When determining the prediction and knowledge that immensely, the Laplace equation is applied. Signal processing. In signal processing, the Laplace transform is materially used. We can investigate a signal processing system using Laplace. For example, multi-value problems describing displacement, coordinate x and t of point of in the string is. So we have these three conditions. Okay. When we apply Laplace transform to the partial differential equation and use property, the equation is we now use initial condition of 30 and 31 and interchange the operation on the right. This equation, right? This equation, so you will get this equation if you use the initial condition of 30 and 31. The ordinary differential equation is subject to the transport of 29. So this is it to become this one right here. A general solution of differential equation 33 is this. This is the general solution. For this function to remain bound as x is near to infinity, we must set a to 0, in which the case the condition below implies that b equals to g per 3s3. Thus, you will get this equation right here. And then where t equals to t minus x per c is the Heaviside unit step function, where this say is the point x in the string falls freely under gravity in this range. So if it is parabolic for this range and horizontal for this range, as to increase the parabolic portion, length, and horizontal section drops. So this is the figure, this is the graph. Next example is consider the following partial differential equation. This equation right here, differential second differential and first differential. The initial condition, and this is the initial condition in the above example. And then use the substitution in the equation of 34, we get this one. Taking Laplace transform equation 36 with respect to x, we get this one. Taking inverse Laplace transform of equation 37 with respect to x, we get this one. Taking Laplace transform of equation 38 with respect to y, we get this equation right here. And that's it for example. So as conclusion, from this paper, we can conclude that Laplace transform is an important mathematical tool for linear dynamic system analysis and design. Laplace transform has a contribution towards our daily life, as does this partial differential equation. Not only this paper discover a lot about this topic, but also significant for both topics, for both equations. So that's all from me. Thank you.
That's all from us. Thank you.